In this video, we will be covering how to calculate the change in velocity and pressure of a fluid flowing through a pipe when it experiences a change in area and height. By the end of this video, you will be able to calculate the change in pressure between 2 points in the pipe and use this knowledge to solve similar problems. Let's begin by looking at the given problem. The problem states that water flows through a pipe with a radius of 0.4 metres. At point A, the velocity of the fluid is 3 metres per second, and the pressure of the fluid is 300 kilopascals. The height of the pipe then increases by 6 metres, and the radius of the pipe decreases to 0.25 metres where it reaches point B. The question requires us to calculate the following. A. What is the velocity of the fluid at point B? And B. What is the pressure of the fluid at point B? We will begin by writing down the information given to us in the problem to help us solve it. It tells us the density of water ρ equals 1000 kg per metres cubed. The acceleration due to gravity g equals 9.8 metres per second squared. R1, the radius of the pipe at point A, equals 0.4 metres. H1, the height at point A, equals 0. P1, the pressure at point A, equals 300,000 pascals. V1, the velocity at point A, equals 3 metres per second. R2, the radius of the pipe at point B, equals 0.25 metres. H2, the height at point B, equals 6 metres. And we are going to find V2 and P2, the velocity and pressure of the fluid at point B. Sub-question A requires us to calculate the velocity of the fluid at point B. We can do this by using the continuity equation. A1 V1 equals A2 V2. The continuity equation tells us that the area and velocity are proportional to each other. This means that one cannot increase without the other decreasing and vice versa. So, to use our equation, we already know that V1 is 3 metres per second, as it's given to us in the question. We can calculate A1 and A2 by using the radii for the pipe at both points. As area equals pi r squared, the cross-sectional area of the pipe at point A is pi times 0.4 squared, which equals 0.5 metres squared. The cross-sectional area of the pipe at point B is pi times 0.25 squared, which equals 0.2 metres squared. We can now add all this into our equation. The only thing left for us to do is to find V2. We can transpose our equation to find V2 giving us 0.5 times 3 divided by 0.2, which equals 7.5 metres per second. We can check that this is consistent with our expected answer. As the cross-sectional area of the pipe decreases by a factor of 2.5, the velocity of the fluid increases by a factor of 2.5 also. Sub-question B requires us to calculate the pressure of the fluid at point B. This can be done by using Bernoulli's equation, shown on screen as P1 plus ρg H1 plus half ρ V1 squared equals P2 plus ρg H2 plus half ρ V2 squared. We must note that, as the velocity of the fluid increases, it will cause a drop in pressure. Similarly, as the height of the pipe increases, this will also cause a drop in pressure. These two changes will result in a significantly lower pressure for P2 than we have for P1. Rearranging Bernoulli's equation for P2 gives us P2 equals P1 plus ρg H1 plus half ρ V1 squared minus ρg H2 minus half ρ V2 squared. We can factor this to simplify it, giving us P2 equals P1 plus ρg H1 minus H2 plus half ρ V1 squared minus V2 squared. Once this is done, we can go ahead and plug our numbers in to find P2. So we know that P1 is 300,000, ρ is 1000, g is 9.8, H1 is 0, H2 is 6, half ρ is 1000 again, V1 is 3, and V2 is 7.5. Multiplying out our brackets gives us 300,000 plus 1000 times 9.8 times minus 6 plus 0.5 times 1000 times minus 47.25. We need to be careful here and remember that a negative value and a positive value gives us a negative value. And so, this equation becomes P2 equals 300,000 minus 58,800 minus 23,625, which equals 217,575 pascals. As there has been an increase in velocity and height, and our value for P2 is lower than our value for P1, we know that our answer is consistent with the expected answer. In conclusion, our value for velocity at point B was found to be 7.5 meters per second, and our value for pressure at point B was found to be 217,575 pascals, or 217.5 kilopascals. So there we have it. We've successfully solved the problem using the continuity equation and Bernoulli's equation. Thank you for watching. Please check the channel for similar engineering education content.